Dr. Brown. In this particular video, we're going to continue to explore rational functions, and in particular, we're going to look at graphing a rational function. One of the things I'd like to say is that we're going to put a lot of emphasis on everyone learning how to use their graphing calculator. This way you won't have to do a lot of graphing by hand, and you can be much more accurate and analyze a rational function much more thoroughly. What we're going to do is learn to analyze the graph of a rational function, and then we're going to look at an applied problem involving rational functions that helps us look at minimizing the cost of, say, making a soda can, for instance. So first of all, we're going to analyze a graph of a rational function. The first one we're going to look at is r of x equal x minus 1 over x squared minus 4. The way the textbook goes is they ask you to look at the zeros, the vertical asymptotes, the y-intercepts, and if there are horizontal asymptotes or oblique asymptotes. And then they will ask you to look at various points and graph them by hand and then try to fill it in. Well, I would like for us to use the calculator pretty much exclusively. The first thing we're going to look at for this graph is, first of all, the zeros. The zeros are when x minus 1 equals 0 and x equal 1 is the only zero for the numerator. The vertical asymptotes are when x squared minus 4 equals 0, or x plus 2, x minus 2 equals 0, which means that the vertical asymptotes are x equal minus 2 and x equal 2. The horizontal asymptote will be y equals 0. Let's go ahead and look at how the textbook would have you do it. They first of all have you put in the zeros. A 0 is x equal 1. Then the vertical asymptotes, x equal minus 2, x equal plus 2. And then plug in a few points in between, and then start drawing the asymptotes and fill in the points and finally get to this graph. Well, I'm going to suggest that the way that this is really done today in the modern world of graphic calculators and computers, that we would put the entire thing in our calculator and then do the graph. And that's the way I'm going to ask you to do it. For instance, clearing the y register, we'll now put this equation in using parentheses. It's very important to use parentheses so that the calculator knows what you mean to graph. Divided by x squared minus 4. And I'm going to go ahead and zoom to the standard window, and then we can zoom in or out as we think we need to. There's a graph. It looks exactly like we have here. We can expand it by zooming in a little bit, going to a window of, say, minus 4 to plus 4, and then on y min and y max from about -4 to +4. And this will show us more clearly the y-intercept, which is 1/4, shows you the vertical asymptotes of -1, a -2, and +2. And shows you the 0 of x equal 1 as we had predicted. And notice that the horizontal asymptotes are y equals 0, happens to be the x-axis. Let's analyze another graph, another equation. R of x equal x squared minus 4 over x. Notice x cannot be equal to 0 because 0 is the denominator. Therefore, there's no y-intercept. There are two x-intercepts where x squared minus 4 equals 0, or x minus 2, or x plus 2, x minus 2 equals 0. So the vertical asymptotes would be x minus 2, x equal plus 2. Notice that since the numerator is 1 higher in degree than the denominator, there's going to be an oblique asymptote. And we can get that very easily by doing long division. The remainder is going to be equal to -4. But the y-intercept is going to be y equal x. So let us graph this in our calculator. And going back to the function itself, plugging in x squared minus 4 divided by x. And since we said an oblique asymptote would be y equal x, let's put that in. And let's zoom to the standard window. Sure enough, there is the graph. You can see the vertical asymptote of x equals 0, the zeros of -2 and +2, and here we've drawn y equal x, the oblique asymptote. Okay, let's do another one. R of x is equal to x to the 4th plus 1 divided by x squared. Let's look at this. First of all, there are no x-intercepts. In fact, no y-intercept, because x cannot equal to 0. And the numerator x to the 4th plus 1 equals 0 has no real solutions, so there are no real x-intercepts. There are, however, x to the 2nd, x squared equals 0 at x equals 0, so there's a vertical asymptote at x equals 0. Notice that as x goes to infinity, the r of x looks like its dominant term in the numerator, which is x to the fourth, divided by the dominant term in the numerator, which is x squared, and that's equal to x squared. So we expect that as x gets very large, the function on the right and the left will approach y equal x squared. Let's graph these. And let's go ahead down here and put in the function that it's going to approach, which is x squared. And then for y1, we'll put the function itself, which is x to the fourth plus 1 divided by x squared. And now let's zoom to the standard window. And we see the graph of the rational function itself. And we also see y equal x squared there, which the function approaches as x gets closer and closer to infinity. Let's change the window now from -3 to +3, and y-min from 0 to about 6. So there's the function itself, and there's the function y equal x squared, which the main function approaches as x gets large. Let's do another one. Let's do the analysis first to sort of see what we expect. R of x, let's factor the numerator, which would be 3x times x minus 1 divided by x squared, divided by factoring the denominator x plus 4, x minus 3. Notice that none of the factors cancel one another, and the zeros are x equals 0, x equal 1. Vertical asymptotes are x plus 4 equals 0, which leads to x equal minus 4, and x minus 3 equals 0, which leads to x equal 3 as a vertical asymptote. And notice the degree of the numerator and the denominator are the same, so the horizontal asymptote would be y equal, the dominant in the numerator is 3x squared, the dominant in the denominator is x squared, and that is y equal 3 is a horizontal asymptote. So we're going to graph the asymptote and graph the original graph. And we're going to notice in this particular case that the horizontal asymptote will sometimes intersect the graph. So let's go ahead and put this in the calculator. we're going to put in y2 equal 3, which will be the horizontal asymptote. And then in y1, we'll put the main equation, which is 3x squared minus 3x divided by x squared plus x minus 12. And let's zoom to the standard window. There you'll see the function itself, and then we drew the horizontal asymptote. Look, here you can't see for sure where there's going to be an intersection of the horizontal asymptote y equal 3 and one of the right-hand side of the rational function, but it sure looks like it is going to. And we also need to look a little more closely around x equals 0 to see what's happening. We know that x equals 0 is a 0, but it looks like it may be going above the x-axis a little bit. So what we do see clearly is at x equal minus 4, a vertical asymptote, and at x equal 3, a vertical asymptote. Looks like there's a 0 here as we expected, and there should be a 0 at x equal 1. What we want to do is look between 0 and 1. So let's look. First of all, change the window from minus 3 to plus 3 and go from like minus a half to plus 1, and we will look at what is happening let's see if we change that window. We didn't change like we'd wanted to. Y min, we wanted to make that minus 1 to plus 1. Now let's look at it, and sure enough you can see the zeros, x equals 0 and x equal 1. See the graph getting just a little bit above the x-axis. Now let's go zoom back to the standard window, and we're going to go look at the graph around the horizontal asymptote of y equals 3. And here we're going to go from about 2 to 4 for y, and go from like 0 to like 70 for x, and go y min minus 1, let's see, not minus 1, y min right below the horizontal asymptote, which would be like 2.5 to right above the asymptote, which would be about 3.5. And now graph it. There's a function itself, and there is the horizontal asymptote. Notice it does intersect, and I believe it intersects about x equals 6. And we can verify that by hitting second calc, putting in the value of x equals 6 and looking at the value of y, and it's equal to 3. Sure enough, there is the intersection, and it goes on and dips below the horizontal asymptote, and then gradually, as x gets larger, approaches the horizontal asymptote of y equal 3. Now we have an example of a graph of a rational function that has a hole in it, and we see that this occurs when there is a factor in the numerator and a factor in the denominator that cancel out. So let's go ahead and factor the numerator, and you can see, going back to the original function, we get 2x minus 4, minus 2 and plus minus 1. Okay, so we got 2x minus 1 times x minus 2. Let's check it out. 2x squared minus 5x plus 2. So we see the zeros are at 2x minus 1 equals 0, or x equal 1/2, and at x equal 2 are the zeros. Continuing to factor, we see that the denominator is x plus 2 times x minus 2. And here we go. There's a factor in the numerator and denominator of x minus 2, which cancels. So x equal 2 is not a vertical asymptote. X equal minus 2, however, is not canceled out, and it is a vertical asymptote. So when we graph this, we expect 0 at 1/2, and 0 at 2. We expect horizontal asymptote of y equal 2, because that's the dominant over the denominant, which is y equal 2. So now let's graph this. Let's plug in y equal 2, which we believe is going to be the horizontal asymptote, and then plug in the function itself, which is 2x squared minus 5x plus 2 divided by x squared minus 4. Be sure you have the parentheses in. And when we zoom to the standard window, one of the things I like to notice is, since x cannot be equal to 2, x equal 2 is not a 0. And we can very clearly see now in our graph that, sure enough, x equal minus 2 is a vertical asymptote. Y equal 2 is a horizontal asymptote. And a 0 is at x equal 1 plus a half. To show that, let's go from minus 3 to plus 3. And like minus 3 to plus 3 on y. And we will more clearly see x equal 1/2 is a 0. Now, I'm going to zoom to the standard window again. And remember we said at x equal plus 2, there's a hole in the graph. Now that's not clear from this graph because the only place there's a hole is at x equal 2, and there's so many points on the graph, you can't tell that x equal 2 is not on the graph. But when we put in calculate value at x equal 2, it will not return anything to us because it knows it can't calculate and divide by 0. So that's where the hole is in the graph. And if you did this by hand, you would actually draw a circle at x equal 2 and y equal 3/4. A circle that's clear, and that means there's a hole in the graph. Now we're going to solve at least one applied problem involving a rational function. And we're going to work this problem, which has to do with an aluminum can that's being manufactured in the shape of a cylinder, typical Coca-Cola can. It's going to have a capacity of 500 cubic centimeters. The top and the bottom of the can are made of a special aluminum alloy that costs 5.05 cents per square centimeter, and the sides cost 0.02 cents per square centimeter. Or really, that's 2 cents per square centimeter. We want to express the cost of the material for the can as a function of the radius of the can, and then be able to graph this and determine what value of R will result in the lowest cost for the can material. Okay, and then what that lowest cost would be. So let's look at the can. The can has a radius of R, a height of H. The area of the top and the area of the bottom with a radius of R would be pi r squared. And then the lateral surface area of the sides would have a height of H, which is the height of the can. And if you took the sides and rolled it out, the length of that rollout would be the circumference of the can, which is 2 pi r. So the area would be 2 pi r, which would be this length times h, so it'd be 2 pi r h. So now, knowing that the top is be 0.05 and the bottom would be 0.05 per centimeter, and then the the lateral area around the can would be 0.02. We can now write an equation for the cost. The total area of the top and the bottom is 2 pi r squared times 0.05 is the cost per unit area, plus the total area of the sides is 2 pi RH times the cost per unit of the sides is 0.02. So when we multiply this out, we get 0.1 pi r squared plus 0.04 pi RH. Well, this has two variables. However, there is another constraint that says that the volume of the can is 500 cubic centimeters. The volume of a cylinder happens to be pi r squared times h. So if 500 equals pi r squared h, we can solve for h by dividing by pi r squared and get that h is equal to 500 over pi r squared. So now we plug for h into this equation, and we get that the cost is 0.10 times pi r squared plus 0.04 pi r times the value of h, which is 500 over pi r squared, which equals 0.1 pi r squared plus 20 over r. And we could just put this in the equation, but if you wanted to, you could find a common denominator, which would be r, which would make the first term 0.10 pi r cubed. Second term would still be 20, and it would all be over r. So this is the cost that we want to minimize. So let's look at this particular equation. I don't know why it was taking a little while to turn on, but it's on now. Let's clear the equations and put 0.1 times pi times r cubed, which will be x cubed in this particular case. And let's go back and put a parentheses. So I just did an insertion. We got to have 0.1 times pi r cubed, rx cubed, plus 20, all divided by x, which is our radius. And let's set up a window. Well, the radius has got to be 0 or above. So let's put x min equals 0, x max Let's go for 10 to start off with. And Y-min cost has got to be more than 0. And the Y-max, say 30. Then graph it, and we'll see where we stand. We stand in pretty good shape because now we can see the cost is going to be minimum at this particular point. Let's put the trace on, and let's computer is running a little slow here. Put the cursor to the left of the minimum. Hit second calc. So we want to calculate the minimum value. When it asks for the left band, bound, hit enter. Then for the right bound, move over to the right of the minimum. Hit enter. When it asks for a guess, hit enter. And notice it tells us that the minimum radius, or the optimal radius, is 3.169, which I would round off to 3.17 centimeters. And the cost would be 9.47 cents. So the least cost can would have a radius of 3.17 centimeters and have a minimum cost of 9.47 cents. Well, that's the end of this particular lesson. I would suggest you make sure you can make all these calculations, and we'll see you on the next video.